Hello, in this video I'm going to kick off the Oxford 2010 mat. So as usual that means the multiple choice questions at the beginning, of which there are 10. So starting with question A, the values of k for which the line y equals kx intersects with y equals x minus 1 all squared. Right, okay, so let's set them equal to each other and then we'll have to see where we get real solutions. So we've got that, expand out your bracket. X squared minus 2x plus 1. So x squared minus 2 plus k, x plus 1 is equal to 0. So we want real solutions for this. So that means we need our b squared minus 4ac. So that would be k squared plus 4k plus 4 minus 4 has to be greater than or equal to 0. So we've got k plus 4 has to be greater than or equal to 0. So we've got ourselves a positive quadratic going through minus 4 and 0, and we need it to be positive. So we've got that bit and we've got that bit. So it needs to be less than minus 4 or greater than 0. And we've got the equals options as well. So what's that? C. Okay, that was a fairly standard A-level sort of question, that one. Nothing very exciting. B, the sum of the first two n terms of this is what? So 1, 1, 2, half, 4, quarter, 8, 8. Right, okay, we've got two series here, haven't we? We've got one which is going 1, 2, 4, 8, 16, and we've got one which is going 1, half, quarter, 8, 16th. So two geometric series which we want to put into our A, 1 minus r to the n over 1 minus r. One of them has got, well, they both got start term 1 for A, so that's fine. We can ignore that. One of them's got r is 2. One of them's got r is a half. So we're going to have 1 minus 2 to the n over 1 minus 2, which is 2 to the n minus 1. And the other one, we're going to have 1 minus a half to the n over 1 minus a half. So that is going to be, right, let's not get this messed up here. So we're doubling this. So we're getting that. That's putting a 2 around there. So we've got 2 minus. So it's 2 to the 1 times 2 to the minus n. So that is going to be, 2 to the 1 minus n. So how is this fitting in? We're adding these together. So we've got 1 plus 2 to the n minus 2 to the 1 minus n, which is A. Okay, so that was fine. Question C, in the range 0, including 0, up to 2 pi, not including 2 pi, this equation has how many solutions? So we've got a sine squared, we've got a cos squared, and we've got sine cos. Well, dividing by sine cos squared seems sensible on this, because then we'll have an equation in tan. So can we divide OK by cos squared? Is cos of x, so if cos x was equal to 0, I just want to make sure we're not throwing away a solution, and we were dividing through by cos squared, then, well, let's just see if cos x is a solution on this, because that would then be 0 plus 0, and that isn't going to be 0 for sine squared, because that would be 1. So we don't have to worry about throwing away a solution. So I'll divide through by cos squared, get tan squared plus 3 tan plus 2 equals 0. So that factorizes easily enough. Tan plus 2, tan plus 1 is equal to 0. So we got that tan x equals minus 2, tan x equals minus 1. Well, they're going to have two solutions each. So 4 solutions. They haven't even thrown in a curveball on that one. Okay, D. The graph of, wow, y equals sine squared the square root of x is drawn in which one? Well, it's going to be, y is always positive, so it can't be a, because we've got something squared there. The magnitude, the amplitude of this has got to stay, this is going to be varying between 0 and 1 all the way along, so it's not going to be this one here. It can't be C. The trouble is if I scroll down, I can't see the function anymore. So it can't be C, because it's not going to be increasing in amplitude. It has to go between 0 and 1. Is the frequency going to be changing? Well, yes, the frequency is going to be changing, because we've got a square root of x. So it's going to have to be B. This is more of the sort of thing you'd see in a physics question. But you can't just keep on getting the same frequency all the time. If you're taking a square root of the x value, it needs to be stretching out, because you're going to be pulling these numbers in. The greater the number, the more you're reducing it down when you're taking the square root. So it can't be d, it's going to have to be b. So I mean, you could even try out a few numbers in order to show the case. You see the difference between having x is 1 and x is 4. That's staying at 1, that's pulling down to 2. And you can see straight away you've got a change in frequency because of that. So yeah, that was one of the easier graph spotting ones. Usually these ones are really horrible. They're fun. I like those graph ones, but they're quite often tricky. Which is the largest of the following 4 numbers? Right, do we know what any of these things are? Log to base 2 of 3. Okay, we don't exactly know what that is. Log to base 4 of 8. Yes, we do know what that one is, because we want to do 4 to the power of something is equal to 8. So if we square root it and then cube it, we're going to get 8. So that's going to give us 3 over 2. So we know what that is. That's 3 over 2. Log to base 3 of 2. We want the largest. Well, it's not going to be that, because that is going to be smaller than a. So we don't really care about that one. And then log base 5 of 10. Right, we don't know exactly what that is either. So how does this compare then? So if we've got 2 to the power of 3 over 2, then how does that compare to 3? Because we want to know what this is going to give, obviously. So 2 cubed, so the square root of 8. Is the square root of 8 going to be less than 3? Well, yes, it is less than 3. So that's less than 3. So that must be a bigger number. So it's not going to be b. And then we've got log to base 5 of 10. So that's going to be the square root of 125. That's greater than 10. So that one's no good. That's less than b. A is more than b. So we'll go then with a. Okie dokie. Right. F. The graph y equals f of x of a function is drawn below for 0 to 1. Okay. Trapezium rule is used to estimate the area. Fair enough. By dividing that into n equal intervals, the estimate calculated would be equal to the actual interval when n, so that's our number of strips, isn't it? Yes, is a multiple of what? Okay, so what bits have we got here? We've got a third, so it certainly has to count in thirds. We've got a sixth there, so it needs to go up in 6. It needs to go up in quarters, and then we've got a quarter again. So we need something that's going to satisfy all of these, which means a 12th is going to be out. We haven't got anything smaller than a 12th, and so we're going to need at least 12 strips. Okay, right, at least we don't have to think about it anymore. That's come out as D. Well, that was a bit of a gimme. G, the function f defined for whole positive numbers satisfies f of 1 equals 1 and also these rules. So to get further numbers, so you can double it. So f of 2 is going to be 2. F of 3 is going to be equal to, that'll be the next one, so 4. All right, okay, fair enough. F of 4, you're going to be doubling f of 2, which will give us 4. F of 5, I don't know if I really want to do all of these. I don't even know what the question is yet. I'm just getting a handle on the series. F of 5 is going to be 4 times f of 2, so that'll be f of 8. Right, okay. So how many numbers satisfy fn equals 16? Right, okay. Well, f10 will, I can tell you that much. That's certainly going to be the case. So we'll have f10. I want a system to this row rather than just saying, I mean, if we do these times 4, then that's going to be another one, isn't it? So f7 will be, f9 will be. So there's quite a lot of them, but I want more of a system than just randomly picking stuff out, unless we happen to hit 6 of them. So what's happening? So each time we get a new number, we're either multiplying by 2 or multiplying by 4. So we could go 1, 2, 4, 8, 16. That would be one way of making 16. And that would be f of 16, because we're just doubling each time. We could go 1, 2, 4, 16. So that would be yeah, we're doubling up, and then we're doing 4 times that. So what number would that end up being? So I would have done f2, so that would be so this is for n equals 1, n equals 2, then n equals 4. So I'd be doing, that would be 9, wouldn't it? That would be f9. That must be how we got this one here. You could do 1, what else could we do? 1, 2, then go 8, then go 16. So we're going to 2, then we'd be going up to 5, then we'd be doubling it to f10. We could go 1, 4, 16. So that would be going 1 to 3 to 7. Okay, and we could go 1, 4, 8, 16. 1 to 3 to 6 to 12. That seems to be, there's no other way we're going to be able to get from 1 to 16 by doubling or multiplying by 4. So we've got 5 options, 7, 9, 10, 12, and 16. So C. Okay, that was an interesting question, actually. Yeah, something a bit different. How to guarantee. I mean, it's nice that they haven't maxed it out. If it had been D, you could have just worked down, or if they'd put 5 as the answer to D, you could have found 5 and say, oh, well, there can't be any more because they haven't given us an option for an answer. But on this, there's that possibility of, well, maybe there's another one. But if you've got a strategy for actually producing these numbers, then you can see there isn't any way to get to a 6 answer. Right, H. Given a positive integer n and a real number k, consider the following equation. So x minus 1, x minus 2, x minus 3, we keep doing that n times, right, is equal to k. Which of the following statements about this equation is true? If n equals 3, then the equation has no real solution x for some values of k. So if n is 3, that's just saying we've got x minus 1, x minus 2, x minus 3 is equal to k. Is there going to be a case where there's no real solution for some value of k? Well, no, that's just not going to be the case. We've got a cubic here. I mean, it's a positive cubic, but that doesn't really matter. But we've got that it's going through 1, 2, 3. So it'll be doing something like that. Now, wherever we go, these just extend on forever. So whatever value of k we pick, there's going to be a solution. So that's definitely not the case. If n is even, then the equation has a real solution x for any given value of k. Right, if n is even, then the equation has a real solution x for any given value of k. But if n is even, well, let's just take a simple even case and say n minus 1, x minus 1, not thinking n, x minus 1, x minus 2 is equal to k. If n is even, the equation has a real solution for any given value of k. Well, again, that's not true because we've got a minimum on this. If n is even, we've got a minimum. So, yeah, we've got a quadratic and k could be down here. So that's not going to be true. Right, if k is greater than or equal to 0, then the equation has at least one real solution. If k is greater than or equal to 0, and the equation has at least one real solution. All right, so what is that telling us? Yeah, what is that telling us? So if we got k somewhere up here, well, for the even ones, we're going to end up starting here and ending there. For the odd ones, we're going to be ending there. That feels like it's going to be true because all of our graphs are going to look something like that with extra wobbles as you're making them, you know, going to higher and higher even powers, or they're going to look something like that with extra wobbles as you're going to higher and higher odd powers. So at some point we're going to cross a positive k. That just has to be the case, it would seem. So let's try and rule out D then. The equation never has a repeated solution x for any given values of k and n. Well, that's definitely not true for the same reason we just seen with B. So you take n is 2, and we've got our x minus 1 times x minus 2, well, equals k. This is essentially k is just transforming the graph up and down. We've got a translation in the y direction, depending on what we're doing with k. You know, if we subtracted it, then it's going up and down. We can just set the bottom of that to be our roots. So, yeah, we can move our, yeah, that's definitely the case. We move our parabola up and down until we get a repeated root. So it's definitely not B, and it fits in with what I was saying about C, that we're always going to hit some positive value. We're always going to hit a negative one for the odd values of n, but for even values, we only hit the positive ones. So we hit positive for both. Right, okay, I'm happy with that. That was quite a lot of thinking. Right, I, 2 to go. For a positive number a, let that integral be that, okay, when di dA equals 0. Wow, when a equals what? So we're integrating to get I as a function of a. So we've got some function, integrate it up. We're going to get rid of our x's, replace them with a's. Then we're differentiating it with respect to a. Okay, we don't really know how to integrate this very easily. 2 to the x squared. I mean, it's pushing to, what it's sort of pushing towards as a first stab, although I'm not going to, this is by no means a convincing argument, is it seems to be saying, well, we integrate it up to get 4 minus 2 to the, well, what would then be a squared, differentiate it back down again, well, whatever that integral is, when you differentiate it back down, you'll be getting this, is what I'm getting at. You know, so we're saying that whatever the integral of that is going to be something to do with a, that when you differentiate it with respect to a, we will then come back to the same expression, but with a's rather than x's. And then say 4 minus 2 to the a squared, as it would then be, is equal to 0. So you'd have 2 squared is equal to 2 to the a squared, which means a squared is 2, and a would be the square root of 2. So that's what I'm thinking the answer is going to be, rather than these various golden ratio variants that they've got in here, or 1. But how can we be sure? Maybe look at the function. What does this function look like? And then see when we're maximizing the area. So we're going from 0 upwards because we've got positive a. So when x is 0, x equals 0, we've got the f of x, if we're saying f of x is equal to 4 minus 2 to the x squared. So f of 0 is going to be equal to 4 minus 1. So 3, okay. So that's a start. So it's going through here at 3, and it's going to be decreasing as we increase our value of x. So when does that equal 0? So it's going to equal 0 when we've got that x squared. Well, it's going to equal 0 when it's at root 2. When x is root 2, we then cut here. So we've got some function that's always going to be decreasing between there and there. Exactly how it's decreasing is another matter. And we want to maximize the area. So it's fitting in with that root 2 again. Yeah, so we're integrating this to get the area underneath the curve. And then we're wanting to maximize that area by varying a. So if we'd set a to be 1, then we haven't maximized the area. If we set a to be 2, then again, we haven't maximized it because we've now got negative area and the integral drop. So yes, so we're definitely coming in at our value there of the square root of 2. Oh, I really like that question. That was sneaky. I wonder if this actually is sufficient then. I don't know. I'm much happier with drawing that graph out. Drawing that graph out really makes it clear about what that question is all about, I think. Right, J. Let A, B, C be positive numbers. There are finitely many positive whole numbers, x and y, okay, which satisfy this inequality if, oh good lord. Right, so if A is greater than 0, B is greater than 1, B is less than 1. So we've got something greater than 1 to the power of x has to be greater than some number times something less than 1 to the power of y. And we want there to be finitely many solutions. Right, well, there can't be finitely many on this because you just have any big x, and that's going to be the case, isn't it? For big x, then, and these are whole positive whole numbers, so we can't even do anything weird with y here. We can't start making this negative. So yeah, you make x bigger and bigger and bigger. For huge x, we're going to have an enormous number of answers. That's not going to be a finite number. So it can't be A. Right, if A is now so we're flipping this around. So we haven't changed anything with what's going on with this side. We're now saying that A is less than 1 to some power, and that has to be greater than exactly the same thing that we had here. So how is this going to work then? So if we've got, well, again, you just need really, really large y. This is the reverse of what we had before, isn't it? If you've got really, really large y, it doesn't matter. You can set x being equal to 1. Let's just say x is equal to 1. Leave that at some number and just make y bigger and bigger and bigger, and this just keeps on getting smaller. So it's not going to be b either. I don't know why we've got these ors in there. Or. Yeah, because that would then be the same. That's the same option then, isn't it? Couldn't they have just written that down and just said b less than 1? Or a, oh, I don't know. I don't know why the or's there. But anyway, I've ruled them both out. Right, C. A is less than 1, so what we've just got here, and B is less than 1. What is the difference between having the and the or on this? Because I've just ruled this out for exactly the same reason. It's the same as the last one. I don't know if I'm missing something here. I can't see what the point is of that or compared to that and. Because you can, providing the A being less than 1 doesn't make any difference on this bit here. And you can freeze it at some small number in the next one. So we can just ignore C as well. That just doesn't fit. So it's going to have to be D. So we've got A is less than 1. And it's to some power. And then that needs to be greater than C being, oh, and then B is now greater than 1 to some power. So yeah, these are now going in opposite directions. So the right-hand side's only going to be getting bigger as you increase Y. The left-hand side's only going to be getting smaller as you increase X. So we are going to run out of values for X and Y that are actually going to fit on this. You're going to get to a point, whatever C may be, where the right-hand side has exceeded the initial value for A, in which case there's no way back. Now you've got a finite number of Y's before that happens. Same thing on this side. You're going to have a finite number of X's that you can use. So it's definitely going to be D. I just don't know why they put these ors in. I really can't see much of a difference between these options. I mean, if you can see something there that I'm missing on those, then put it in the comments. But I don't really see that they're making much of a distinction there between those different options. They just seem to be getting ruled out for exactly the same reason as each other. So I don't know, maybe I'm just missing something, like I say, in those in that part of the question. But D is definitely going to be the case, because if they're both pulling in opposite directions according to this inequality, that one's getting bigger and that one's getting smaller. Eventually, yeah, we're going to run out of values of X and Y that are going to make that possible. So I'm perfectly happy with D being the answer. I'm just not very happy with A, B, and C as being potential options to solutions. So anyway, that's the 10 questions. Don't think much of J. I was a great question. H was quite good fun. G was all right. That one, F, was really easy. E, they do those quite a lot, and providing you know how to manipulate logs, they're all right. D was a quick one. C was a quick one. And A and B were quick ones. So they've thrown a nice chunk of relatively easy ones in there, but then they've thrown in some horrible ones at the end. So yeah, it's sort of one extreme or the other maybe with this set of questions. But hopefully you found some in there that you've found okay, and it's helped out with some of the others.